Hi there. So now let's do the analysis of the time series. So again, you will have in the course website, but also in the team channel, I will put all the time series. If you didn't run to up to the latest standards, you don't want to run, you can download the time series. So basically in the case directory, in my case, I will go back to the case I just run. See that you have these files. Okay, you have CD, CL, this name that you see here, you gave this name. So usually it's .out, the extension that Fluent use. But basically it's an ASCII file. See that I open it? So this is a very standard file. So here you have iteration, the value, and the time step, and the same iteration, value, and at the end you have also the time step. Okay, iteration, time step, and the value for each of the probes. Okay, so it's a standard file that you can format, you can put it in this format, you can do the time series analysis in Fluent, but also you can do it using any other application. I like to do it using Python, using in particular pandas for those who knows what is panda in Python for that analysis, but it's up to you. You can use MATLAB, whatever, or Excel, but let's do it here in Fluent, given that we have the utility and it works well. So since to do here, like, see that to do this data analysis, you go here, and here you have this tool, the FFT. Remember that FFT that we need to do, plot the energy spectrum and everything. Here you can plot also the signal, okay? So as you go here, so you can plot this same time signal that you see here, you can plot it here. So for instance, if you go here and load, you look for the file, so see that is CD, the .out, okay? So for instance, let me open CD. You load the file, so see that it's loading the file. So by the way, it's called CD. Remember, when you create the monitors, you're giving those names. So see that report here, see that is you enter here, see that I'm calling that one like this, is you open that one. When you create the files, you are going to give the name, okay? It's up to you. If you don't put anything, Fluent will use a default value. I don't recall, but it's always a good idea to put up a name that you can easily identify. So see that I load here that file, and now I can do the plot. You can plot the FFT later. I'm going to show you, but I want just to plot my input signal. So if you click here, you go to another window and you apply plot, and see that here you have your time signal. So let me go a minute, because here, let me put it, so very often you can have something like this. So see that at the beginning you have these strong peaks, no, the initial transient due to the initial conditions, and then since stabilize. So to adjust axis, here you go into axis, and here you can choose X or Y axis. So in my case, I want to adjust the Y axis, deselect auto range, put your values there, and voila, you are there. So this is your time signal, okay? So this is the CD. So see that you have an initial transient. So later we're going to run the 2D, and in 2D I will show you how long it takes to unset this one, okay? Because here we were using the non-uniform initialization, the perturbation. But see that initial transient, and then everything becomes kind of periodic. So see here that if I want to compute the mean value, probably I will go 40 to 80. So see here that it's already giving you all the statistics, the main statistic, no? Minimum, maximum value, mean value, variance, okay, the number of points, giving you also minimum frequency, some other values. So for instance, you can say click to range, and I want to click for 40 to 80, apply plot, and see that you have your plot. And now you have here the new statistics. So this is what you are going to look. So see that you have minimum and maximum values, and your mean value is something about 0.95. If you go to the experimental results, remember I mentioned that there is a lot of experimental data. So for this trainer, which was 1,000, it can be anything between 1 to 0.9. Okay, there is a lot of uncertainty in the measurements and the CFD, but we're within the range. Okay, so you have variance, the number of samples. Okay, this is related to sample frequency. Okay, so if you want to know the times, it will be the inverse of that one. What else we can get for that one? So it's a very useful tool. Okay, I like it a lot. Okay. It is embedded here. So see that, for instance, you can do also choose window. Later we're going to talk about this, but here you get your basic statistics, okay? Any signal you can put here, okay? Even the points that we saw later. So for instance, let me now plot another signal. So I would like to plot the lift coefficient signal. You go here and the same, apply plot, and see that again you have the problem with the axis you need to adjust. So just here it will be safe to put auto range and see that you have your axis there. You can again click to range and you go like this. Apply plot, and this is your signal. So here you can compute the frequencies, you count here, you can get the frequency just by counting peaks, but we have the FFT function now that we can use it to find the dominant frequency, okay? Sometimes it's not as clean as this, or it's trickier. So also is the one you can subtract the mean value for that one, okay? There is a lot to do, okay? So divide into segments. So there is a lot to do, but this is the basic stuff to do the signal processing. So just to show you also the one for the points, you have it here. So let me see, for instance, this one, okay, vertical velocity, and that one. See that in this one we're saving a lot of information. We're saving like 8 probes that we put there. So you have all the information. So see that what is really nice here is that when you do this here, you can access the probes. See here that you have access to all the columns. So you say that I want to plot the probe 8, apply, and this is the signal in probe 8, or you have here probe 1, the signal in the probe 1. Okay, and for each one you will get the statistic. In the same way you can click to range, okay, and that's all. Okay, so let's say for instance now that I want to find dominant frequency of a particular file. So let me load another file. So usually remember, all these files are copied, are saved in the directory where you are running in Fluent standalone. If you decide to run for Workbench, look in the files that everything is hidden in your data structure. But okay, let me open, let's say CD. I go here, plot, you have that signal. Let me adjust the axis. Okay, apply, you have it there, and let me subtract. So I leave there that, okay? And for instance, here now we move here, we're in Fourier transform. So see that you have different options here, okay, magnitude. So I'm not going into it theory, okay, later also probably we're going to visit a little bit in pandas when we do, but I was post-processing in Python and stuff. But see that you can compute frequency, structural number, that stuff. So let's go into frequency and plot, and see that you have this plot, okay, you have all the frequencies that you see, but see here that we need to reduce the range here to see the dominant frequencies that we have. Okay, so let me put this one, apply auto range. So this is what we have, and clearly see that we have here, we see a dominant frequency. So if I go here and I adjust my x-axis, let me see frequency from 0 to 2 Hertz. So in this case, depending on your physics, you can have very large frequencies. So see that clearly it's telling you that you have a clear frequency here, something about 0.48. Okay, you have a dominant frequency. Okay, so let me go back here. Okay, and again, you need to play with the axis here. Okay, so as you go here, this can be a little bit annoying, and as you count the peaks, you will see that you will find that frequency. But see that when doing this analysis, we were also counting the initial transit, and this can add some noise into that signal. Okay, so now let me go and get this out from 42. So now it's very clean. So this is why it's important that you need to gather statistics and see where you need to do your sampling. So see that now I'm not using that dirty information of the beginning. I have everything very clean. And if I go back here and I do this again, see that now it's very smooth. Previously, remember that you have some noise here at very low frequency values. See that now you don't have that anymore. And you can go here and adjust this and show me, well, I know that 0 to 1, and see that you have this very clean signal. This is a precise frequency that you are capturing there. So let me go here, auto range. See that you have this precise frequency at 0.45, and previously you have some noise, we were having some noise. So now by erasing that initial transient, you have a very clean signal. But what is interesting is that probably here you have another frequency here, very small, and another frequency here, also very small. So as you see the videos, maybe you will see that there is some vortex shading, something that you might be capturing there, that you will see that frequency here. So see that it's not perfectly symmetric, okay? So maybe you will see in those, we're seeing those frequencies as well, but you have a clear dominant frequency, okay? So if I go here, for instance, now, the Strohal number, and you plot this one, now you can get the plot for the Strohal number, okay? So see that now you have there a clear Strohal number. This one is computed using your inlet values. Remember that there is a Strohal number definition that have a value, inlet velocity. So see that we have this Strohal number, okay, but we're using the drag signal. So as you go back here, let me go back to the slides, and this is something important, not always, but also when you analyze data, you should look what you have. So see that as you look at these two frequencies, you realize that this frequency, the drag, is twice the one of the leaf. So there is one that you should, this one will give you twice this result. So it's likely that the leaf signal will be half this value. Okay, and usually we look at the leaf signal. Okay, so what is happening when you look at the okay, let me look here. When you look at here, no, let me look. This one is okay. See that you have a vortex separation for top and bottom. Okay, so that separation for each of the signal of leaf or drag, you are going to have a different behavior in time. So usually what we look at is that the, okay, this is the mean value. So probably let's look here. So see that the shading, and you have a vortex separating from here and here, and this vortex separation you will see a higher frequency in drag, okay, and the leaf frequency will be half of that, okay, due to the vortex shading, okay, that you see here. Those frequencies in this case, see here, this is half of this. So usually we look at leaf, okay, at this leaf frequency, or if you have lateral 4, also the lateral 4, but drag frequency will be twice. So see that if I move from this frequency to the other, so now let me move to leaf. Again, you can plot your signal. Let me adjust here. Whoops, clicking help. Okay, so you well, just remember that you also have the help. You have everything there, so you can, I'm strongly encouraged to click there and visit your help. So see that you have your signal. It's also clean, but again, let's do the same. Let's plot from 40. Okay. By the way, when you do this like this, you can also write this data in a format, okay? And then you can pass it to another software, or read here a cleaner data. And here you see that you have your statistic. We know that this case is symmetric. Leaf should be about 0. So see here that there is some noise, but there's no problem. This is a very low value, and you have kind of a symmetric signal. Everything looks fine. And when we go here, plot signal, okay, sorry, plot the FST, but let me go back first. Here I want to have again the frequency. If I plot this, see that now again a clear frequency dominant here, and let me adjust here from 0 to 1, and see that this one, as you recall, this one is half the other one. It's a very clear frequency, something about 0.22, whatever. So if I go here in the Strohal number, and if I plot this, see that this is half. And there is a lot of theory, just to remember, and if I go to the beginning here, see that we know that the Strohal frequency here, this results, is something about 0.2. So you can average, you have different values, then you go to this region that is a little bit critical. Now you have a crazy vortex shading, but see that as you go in values from 100 or 200 that were, let's say, in turbulent regime, okay, up to probably 100,000, see that your Strohal number is something about 0.2. And see your drag also here, you have it. So see that our values are okay. So, but be careful that probably if you take a look at that drag signal, you will say that everything is wrong. So look at that, be careful, look at your signals, analyze all your signals. So you get it from here, and that's all, okay? We have the post-processing. This is the, let's say, the very handy, this utility to have it here, okay? Otherwise, you go to you need to go to another external software, but post-processing this in external software is very easy. And actually, I prefer to use Python. As I mentioned later, I will give you some scripts of my own, but you can write it. And the final part I would like to do is now, let's read another data, the point data, okay? So let me read this one. Okay, plot signal, and let me plot the signal at this one. Okay, and axis, let me just this. So see that we have this signal, see that this signal is a little bit crazy. You look at that, you have this strange behavior. Again, we have this, and from this signal, again, you can compute frequencies, okay, but also we can plot the power spectrum, the power spectrum. And remember, that is the call to get the Kolmogorov law, the one that he predicted in -5 Serge. But to do that one, you need to get turbulent kinetic energy, okay? So that is later, we're going to go into details. Here we have the instantaneous velocity. If you want to get the turbulent kinetic energy, you need to get the fluctuation, and remember that fluctuation is instantaneous value minus the mean value. And remember that we're computing statistics, so you can do mean instantaneous minus mean, and you get that fluctuation that actually you have it here. So as you go here, subtract mean value, see that you are subtracting your mean, and here you have, this will represent your fluctuation. But in this fluctuation, also you have some peaks that you need to detrain this data, okay? So this is something particular, later we can talk about that, but see that we subtract this one, so in theory this should be the fluctuation, okay? Or the fluctuation, and then you need to compute the turbulent kinetic energy, that is this square plus all the components or whatever, or you can get the 3D spectrum or the 1D spectrum. And because later we work on that. So see that in this case, you can do the same analysis, so you can plot here, for instance. See that now here you can get, is a plot, sorry, let me go frequencies. See here that you have different frequencies here. You have two clear dominant frequencies. So let me put this too. So see that you have a frequency like 0.2, but then you have another frequency, a much higher frequency here. So as you go back to your signal, it's clear that will be here and here. See that you have the clear between the large peak, but the other higher frequency is this one. Okay, so see that you can detect that all those frequencies. So doing this now visually, it becomes trickier, and sometimes these signals can be very, very non-uniform. Here you see that you have kind of a periodic behavior, sometimes can be very non-uniform, so it's not straightforward to count that visually, okay? So this is the advantage of doing this kind of signal post-processing. So for instance, now if I go here, and remember to plot that power spectrum, you need to do it here is linear scale. So as you go and you put this one, now you change your axis and you say I want logarithmic, apply, logarithmic, apply, and you plot this one. See that you have something that resembles what we have seen. This is not properly that one, okay? But this is how you can do also the energy spectrum influence. So you need to get your turbulent kinetic energy, put it there, and you get this plot. So this frequency, remember that you have the reciprocal to this one, that will be the wave number, okay? So remember, smallest vortices or scales have the largest frequencies, okay? And here we have large vortices, small vortices, small scale with really high frequencies, okay? So this will be your cutoff frequency. So you can know this cutoff frequency because you know also the dimension of the cell at that point, okay? This is how you can analyze that data. So as you put here the -5 Serge, you might or might not get that one. I'm not sure in this case because we are not precisely getting all the turbulent kinetic energy, but this is how you do it here. Again, also you can change this plot. So see that it's important also to use time, okay? So you put time step there, you get something different that is not right, okay? So you need to use flow time. Okay, important. Actually, no, it's okay. This is important. You put times that we have this, but what I also like to point out that this analysis also, it is extremely recommended to do it using a constant time set. So as you recall, I ran my simulation using this constant time set. I recommend you to, when you do unsteady, to use a steady time set. It's much better, okay? Because when you do signal post-processing, it's better to use constant time set. However, there are some specific techniques to deal for that, but much better to use constant time set. I'm not going to talk about this, but here, for instance, if you wonder, you can use adaptive time step and CFL base. So you can say that I want to run for a CFL of 10, and then Fluent automatically will adjust your time step to reach that one. I don't recommend you this method because you have a variable time step that can introduce perturbations in your solution, and we have seen that those perturbations can trigger some instabilities. Okay, and it might be critical when running turbulence cases on a steady, and especially cases where you have transition. So it's much better. So, but if you want to know how to use this one, go to the help, but go and fix your time step like this. Okay, so at the beginning, it is an iterative process that you need to guess it, but I gave you the guidelines. So finally, also you have the options here when you are doing acoustics. This kind of post-process is very important in acoustics. Just to mention that I go here, also you have these options to create windows, to remove noise. So you have different techniques. Also, this is a standard theory for signal post-processing. So just dust your books, your notes, and visit that one, because I might address this when we go into the specific post-processing. But also you have the help there, so you can choose a technique and you apply some window technique there, and plus this one. So see that you get different behavior, but it's just kind of cleaning your data, preparing your data to have a better post-processing. So see that if I choose different points, see that you get different power spectrums, okay, as expected, because in each point you have different information passing, smaller, larger vortices, okay. So see that each one will give you, and the one that is farther away, you will have something like that. Finally, just to mention, this is the signal post-processor, but to go back to the case and to stress this again, remember that we're running, this is 2D, even if we put the one cell, but this is 2D. Remember, 2D simulations, they are very, very energetic, okay, because you don't have the vortex stretching. And remember that that is very important. We have to talk about that. So when you go to 3D, you will see that usually all this energy, everything is lower. This doesn't mean that it's wrong, but it is the right behavior because it's less energetic. Okay, you have the actual physics, you have the vortex stretching, how the vortices dissipate, the separation, how all this is scaled for. Instead here, you don't see that vortex stretching. So that's all for this post-processing. Okay, so you have this very useful tab. Okay, you can plot everything. So that's all. Thank you for your attention. See you next video. Bye.